Hello, discrete math fans. Let's talk a little more about Pascal's triangle. Remember that we said that the kth entry in row n is n choose k. And remember that we have this formula. N choose k is equal to n factorial over k factorial n minus k factorial. Now, as you look at the triangle, one very obvious property it has is left-right symmetry. We're going to express this fact with a theorem. Now, right now, we're going to prove this algebraically. And later, I'd like to come back and prove it the right way. Now, the algebraic proof is going to be messy, but very straightforward. We won't do any difficult algebra. It'll be sort of complicated looking, but it also will not be very illuminating. Now, when we come back and do this the right way, it's going to be a little harder to understand, but it will be much more illuminating than the algebraic proof we're about to do. All right, so the theorem is that for n and k, that are whole numbers with n bigger than or equal to k, n choose k is equal to n over n minus k. So that's the left-right symmetry that we're talking about. Let's let n and k be whole numbers with n bigger than or equal to k. Then, as we know, n choose k is equal to n factorial over k factorial n minus k factorial. Now we're just going to do a little bit of algebra. We'll just swap the order in the denominator. Then the k factorial on the right-hand side in the denominator, we'll rewrite that as n minus the quantity n minus k. And of course, by definition, this works out to be n choose n minus k. And that's the end of the proof. So really, it's just a bit of algebraic manipulation. Nothing particularly exciting, but also not very illuminating as to why it's true. And as I said before, we're going to come back later and give a different proof entirely. Now, we previously talked about the construction of Pascal's triangle. Each interior entry is the sum of the two entries above it. All right, so as an example, in row 8, the number 56 comes from adding the 21 and the 35 that are above it. The number 56 is entry 3 in row 8. So what we can say is 8 choose 3 is 56. Meanwhile, the numbers 21 and 35, they are entries 2 and 3 respectively in row 7. And so that tells us that 7 choose 2 plus 7 choose 3 is equal to 21 plus 35. That means we can say that 8 choose 3 is equal to 7 choose 2 plus 7 choose 3. And every entry in the triangle is constructed this way. So that gives us a general formula. So this is called Pascal's formula, and it says that for n and k, which are whole numbers, with n bigger than or equal to k, n plus 1 choose k is equal to n choose k minus 1 plus n choose k. And like the previous theorem, we're going to prove this algebraically. It's going to be messy and not very illuminating, but the algebra will be very straightforward. And then we're going to come back later and prove it the right way. Now, as we go through this proof, I want you to just follow along with how messy it is algebraically. The right proof is going to be conceptually more difficult, but we won't have to deal with any messy algebra at all. All right, we'll start with an n and k, which are whole numbers, n bigger than or equal to k. And then just using the formula, we'll replace n choose k minus 1 plus n choose k with these expressions. N factorial over r minus 1 factorial, n minus r minus 1 factorial, plus n factorial over r factorial, n minus r factorial. All right, now we got a bunch of algebra to deal with. First of all, let's take this expression here and fix that up by distributing this minus sign here. All right, now we've distributed the minus sign, and now we're going to make common denominators. In order to do that, we'll have to multiply both fractions by 1 chosen in the right way. The correct choice for the first fraction is going to be r over r. For the second fraction, n minus r plus 1 over n minus r plus 1. All right, so a little hard to see why that's going to be the right thing. In just a moment, we'll see how multiplying by these expressions will be the exact right thing to get a common denominator. Now we moved things around a little bit here. So this r right here just got moved over here. And there's some color in here, but we'll worry about that later. This particular n minus r plus 1 just got moved down here. And again, there's some color that got moved in. All right, now let's talk about the color. Take a look at these two expressions. The one on the left is r times r minus 1 factorial. That's just r factorial. Then on the right, there's n minus r plus 1 times n minus r factorial. That's just n minus r plus 1 factorial. We're out of room here. I'm going to go to the next page to continue this calculation. Okay, so those blue expressions in the denominators of the previous slide got combined into factorials. You'll notice now that we have common denominators. Yay! Also notice in the second fraction we multiplied things out, which, since we have common denominators, allows us to do some canceling. Okay, now let's put things together into a single fraction. All right, we have a single fraction. So the numerator has an n times n factorial plus 1 times n factorial. Let's go ahead and combine that by factoring out the n factorial. So the new numerator is n plus 1 times n factorial. That, of course, is just n plus 1 factorial. And now, this final expression that we have is simply a binomial coefficient. It is the binomial coefficient for n plus 1 choose r, and that's exactly what we were trying to get to. Okay, that's all for now.